Okay. Today we're discussing autocorrelation and time series data. It's an extension of yesterday's introduction to using Pandas for manipulating and working with data associated with dates. Today's lesson will be fairly straightforward without a lot of conceptual new terminology or new models or anything like that. It's just how to do things that you would likely anticipate being able to do to analyze data associated with time in Pandas, specifically related to the concept of autocorrelation. So with that said, we'll just do a quick review of like what time series data is, why we care about it, what trends and seasonality mean, what autocorrelation is from a theoretical and mathematical standpoint, and then the majority of our time will be spent going through code that I've shared in the repo about how to implement these principles. So you can think of this as like exploratory data analysis using Pandas on time series data. Fairly straightforward. So first and foremost, you guys had an introduction to time series data yesterday, but a nice concise definition from Penn State Statistics. It's a series of measurements of the same variable collected over time. And typically these measurement periods are at regular time intervals, whether that's days or weeks, perhaps even once every quarter, if you're talking about GDP data, or once every month if you're talking about employment data, things that vary over time in a consistent amount of elapsed time. What are some real world examples where time series data analysis from an exploratory perspective may be useful? I give a few. I mean, GDP is released quarterly. Employment data is released monthly. What are some examples that you all have encountered or think you will encounter?
Both default rates, depending on time period. It's sometimes bi-weekly, sometimes monthly.
Is that data reported bi-weekly, the number of people that have defaulted?
On that, it depends on the company.
Yeah.
On that reports bi-weekly and sometimes by the day.
Cool.
Cat One and other major vendors, lenders report by month too.
And okay, so it's like every month, here's a list of the same companies and whether those companies have defaulted?
Yeah.
Cool. Yeah, so I mean, even in the broader perspective, finance. Time series data analysis is huge in financial analysis because finance measures just about everything and, you know, down to the millisecond. Other examples? So we have finance, we have economic employment data and GDP. What else? Yeah, census for sure. Yeah, climate change. Yeah, perhaps disease spread over time. Yeah, epidemiology. And then the last one ties into economics, sales data. It's pretty commonly reported by quarters, months, etc., and will likely be something that you see as a data scientist. So the concepts of trend and seasonality are probably not super unique and therefore new to you in this course. So let me ask you, what constitutes a trend in data that we've witnessed? What constitutes a trend? Yeah, a predictable pattern of variance. Particularly, we may expect one direction or another direction, or at the very least, even if it's bidirectional, follow some function that we could map. Yeah, and then for everyone, is linearity required for a trend? Raise your hand if you think yes. Raise your hand if you think no. Who's unsure? So linear trend.
Like the trend is.
Yep. Is that required for us to witness a trend? No? No, it's not. I think everyone's like on the right track, but doesn't want to quite jump in the pool. Yeah, it's not required. By the same statement that I noted, perhaps we have a trend that maps like a parabola, or yeah, something of the sort. You can think of companies that, you know, did quite well, peaked, and then had decreasing margins or revenues. That could be a trend in our data, and it's nonlinear. So here's an example of iPhone search volume on Google, and we can see this trend increases and also spikes around particular moments. And those particular moments that it spikes happen to be around, you know, the release of an iPhone, because people are Googling and checking out what the new iPhone looks like and what minute change will cause people to spend hundreds of dollars for a new device. And so this also introduces the concept of what seasonality is. So can someone think of a definition of seasonality and how it would relate to iPhone search volume on Google? Yeah.
Your recurring pattern that happens at the same time of the year or around multiple times of the year where it's that occurs. So the iPhone, then all of these products.
Yeah. Yeah. And the key thing I like about your definition is you say the same time of year from year to year. So seasonality can be thought of as patterns that happen over fixed periods of time. In other words, the same way, of course, that there's 4 seasons a year and they begin at the same point each year, that's where seasonality derives its name. But we're not limited to solely just seasons of the year. We could have, you know, every week we have the class time on a Monday is much higher than class time on a Sunday, for example. We have a regular pattern that exists, and we can map that pattern and identify it. And that will be valuable for us later when we think about doing time series analysis, because seasonality could be something that we'll want to control for, causing regular spikes in our data, which I think you'll dip into tomorrow. And so iPhone search volume example can kind of be like a red herring, because the iPhone doesn't come out at necessarily a regular interval every year. Typically, I think Q3, but not necessarily always Q3. So yeah, the last concept that we want to introduce is autocorrelation. And actually before, we don't need the scary math guy yet. So autocorrelation is this concept of the same thing as what we've been dealing with in terms of correlation, in terms of saying how much does a change in X move in the same direction as a change in Y. Not a regression, just seeing how much the two move together. Except with autocorrelation, we're going to check how much one thing moves relative to itself. And the way we do that is we set a lag, where the lag is a number of time periods that we're measuring. And we see how many or how much a time in the past correlates with today. And that's in essence what autocorrelation is. We can measure how much one variable moves relative to itself at a different time period, thereby just measuring how much a variable moves relative to time itself, because that's the only thing that's changing. And in doing so, identify how closely earlier observations imply things about future times. So at a high level, autocorrelation is just being able to measure how something is changing over time. And in the same way that correlation is measured -1 to 1, autocorrelation is also measured -1 to 1, where 1 is perfect relationship, -1 is perfectly opposite. Yes. Yes. So autocorrelation is computed by simply setting some lag k, and then calculate the difference between time today and that time at k period. Fairly straightforward. The key here is we can set our k, right? We can say the lag is 1 day or 7 days, or maybe even 365 days if we want to see year-over-year autocorrelation changes. Yeah, that's pretty much the gist of each of the concepts. So with that said, we'll go straight to the repo now. And there's a lot of ways to manipulate data with time that we're concerned with. And that's the crux of today's lecture. So the code or the data set we'll be using is by a German drugstore, Rossmann, and it contains the daily sales of a bunch of stores over a series of years. And we'll want to look at things like, how did holidays affect those sales? What about days of the week? How did it change from year to year? How much does sales of the previous week correlate with sales of the next week? And things like that. So again, as I noted at the top of this lecture, it's largely exploratory data analysis with time data. So first and foremost, we're going to be sure we have classic pandas and seaborn, so we have some plots. And then we're going to read in our data. And let's take a look at what our data looks like so we know what we're dealing with. A huge data set, so it takes a while. An important consideration when we look at time series data. Depending on the trend we're trying to observe, remember how previous data sets, time wasn't necessarily an absolute consideration or even factor. Of course, that's what delineates what we're doing today from previous data analysis techniques. Therefore, if we're trying to do some exploratory data analysis of time series data, taking a random sample or a random subset of that data would make less sense than, say, taking 1 year or 2 years and looking at how trends exist in those 1 or 2 years. In other words, if you imagine taking a random set of rows of our data set, you'd be taking a bunch of random dates. And that's not very useful for us to consider how things are moving over time if we don't even have a consistent unit of measurement. In other words, we're tossing out the value of time series analysis by eliminating the definition, a regularly measured at a constant interval set of observations. That's notable because we'll work with just a subset of our data. So here you can see we have the store, what day of the week it was, the date, the number of sales, the number of customers they had, if the store was open, 1 or 0, if there was a promotion, 1 or 0, if it was a state holiday, and if it was a school holiday. So very simplistic data set. Okay, so we're going to go ahead, and this is incredibly common when you're working with time data. So you always remember that we have an index call, right? Where it's just like that 0, 1, 2, 3, 4, 5 that we see on the side, of course, that like has no actual observed bearing on our data. It's very common with time series data to make our index be the date, because the way that our data is organized is already by date. So inferring or setting our index equal to that date kind of just makes sense, so that we can refer to one period of time by just referring to one specific date in time. And of course, that one date is going to correspond to a row in our data set. So first and foremost, I'm going to be sure that our date column is converted to truly a date time object. And then I'm going to set our index to date, and in place is going to be true, which means the date from a given spot is just going to be moved over to the index for that spot. Non-unique indices?
Yeah, because there are multiple entries like per date, or is it like those are so specific, like the hour or something?
We actually only have the sales data per day.
So the fact that like you have repeating indices is not a problem.
No, we don't have repeating indices because each row is a day in time. I'm inclined to believe It wouldn't let you set that as an index.
It's just, if you look at the head that you printed out, I think it's all the same data listed. I guess, I think what Cody is saying is since it does get so granular, like down to the microsecond, even though you don't see it there exactly, that like actually inherently different set of heads of index.
No, okay. So what we're doing is we're taking the date object of each row, and then we're in a sense sort of grouping in a way so that we can grab one year and it's going to have all the rows associated with that year. In other words, non-unique indices will not throw an error for us, but instead will not refer to a single value. So what's that?
Like making the non-unique allows us to do that.
Hold on to the group by thought. We're going to do something different instead of, so like group by makes sense when you have categorical data, but when you have dates data, we'll do a different thing called resampling, where we're going to either take the mean of everything on that date, or perhaps the median, or perhaps the sum, and that's the equivalent for group by. So when we just set the index, we're just saying that these indices are equal to some date. And if we call that date, which has multiple indices on that date, it will spit out all of the rows corresponding to that date and time. So for example, here I'm going to go ahead and create a column called year and a column called month. Now I'm going to show you our data frame, which has non-unique indices. However, I can refer to one date in time. Here I did 2014, and see all of the single row sales data by store on that date. Or if you saw in the head, I created these columns here, year and month. And I was able to abstract those because this was a date object. So calling the year on index, Pandas knew that since index is a date object, asking for year will in fact return whatever year it is, in this case, 2015 for this value. So that's the valuable thing about setting date objects. But so here when I grab, I just did this. When I show you 2014, even if the index is not unique per row, the index will refer to every single store or sale that happened on that given day. In other words, we wanted it to be not unique in this case because we care about each year or each day of sales. And so I can do the same thing by saying, I just want the May of 2015 sales data. And you can see date is our index. It's indented on a different row. And then you have all of our other data points. And so as I alluded at the very beginning, if we took a random sample of this data, it would not make sense because, well, random sample for the purposes of exploratory data analysis wouldn't make a ton of sense because then we would have a bunch of days that are not necessarily uniform, and therefore we would have a bunch of days that aren't measured over the same period of time. For example, if we just took a random sample of 100 days, we're not taking a random sample of a continuous span of those days. We'd be taking like day 1, 6, 8, 9. Therefore, to do our exploratory data analysis and make this a bit more manageable, I'm going to, in a moment, take a subset of our data from a specific year. And here I'm going to take a subset of our data that's only store 1 in all of our data set. I'm going to call that store 1 data. So of course, store 1 data is the exact same as our other data set. It's just called store 1. Okay. So now all we've done is we've loaded our data, got our appropriate libraries, and set up some data frames to do some analysis. So the first thing first thing is I wanted to consider how, in the form of a visual, so I'm going to do a box plot from Seaborn, the similarity between how sales compare on school holidays in our given data set. So I'm just going to use a factor plot, set my x to school holiday, y is the number of sales. The data is going to be the data frame I've just worked with, and the kind is a box plot. So we see here from that, there's not a big difference between a school holiday or not and its impact on drugstore sales. We could do the same thing for promotion days. And note that I'm also grabbing the column open here, which means that I'm only limiting my results to when a store is open, of course, so that my data isn't skewed towards promotions on open or closed days. It's only truly the days that there could be a promotion. So you can see that the promotion does impact our sales. And you'll note that Seaborn created an open equals 0, and we have absolutely 0 sales on that filter. That makes sense. We can't have sales if the store isn't open. And then that's just what I commented here. Like, we care about things being open. Context matters as data scientists. That's the crux of exploratory data analysis, right? Is checking your assumptions versus what the data may say and applying context. I can do the same thing for days of the week. Okay, now let's do things a bit more interesting. Let's see how sales changed between 2014 and 2015. And what I'm first going to do is I'm going to create a data frame of the days when store 1 is open, because that's truly all I really care about anyway throughout this analysis. So the way I'm doing that is, of course, declaring a data frame and then applying the filter of equals 1 for the column open. So only the days that the store is open are being in this data frame. Now I can make our first plot over time, and I'm going to do it of sales. So we can see, of all the years in our data set, what does the sales data look like? So what do we observe here? 2 spikes at the end of 2013 and 1 at the end of 2014 in sales. Maybe we'll find out in a different way. But yeah, so I'm going to do the same thing for customers. And would you expect this plot to look similar or different? Similar. Unless there's just like some days where the same number of customers go and just buy a ton. Oh, that would make sense. Everything checks out. Oh, wait. Okay. I have this exercise here, and I already have the answer, but you don't. So I want to see the trend for the year 2015 only, is the exercise. I mean, you can do just store 1 again, if you like. So how would does everyone understand what the ask is? The ask is to produce this plot of sales for only the year 2015 for store 1. Yeah. So I would actually just use the data frame we created, store 1 open data, work from that. Oops. And I think when I did this, I actually did everything. I think I did all scores. I'll check in a second, but the point of the exercise is not to see the actual answer, but to try to do this, obviously. What data frame you work with will not change much of our code. Who's kind of stuck? Good.
Sure did.
Nice.
Much earlier than I usually do.
Yeah, the cultural context.
Yeah.
Beautiful place.
No, my voting location is online.
Go ahead.
This is the South Street. So
Yeah, I went there last year. For primaries.
you're so nice.
Oh.
You can do what the choices are. So you can do it for all stores, you can do it for store one data, but whatever you like to do. Yeah.
Now it's using still
Yeah.
Our analysis is correct.
I thought though. Oh, yeah, it's not, it's the one. Yeah. Oh, so they can actually do this.
Yeah, that's the results of 25 years of 25. Pretty sure.
But I know.
You actually told about this. Oh, yeah, here you are. Here you are. Yeah, here you are. Maybe they thought that it was
Yeah. Who's in on contact? And just like 8.
I'm pretty sure, yeah, once this course is done.
I think everyone sorted it out. I think everyone got it pretty well figured out. I created a different data frame when I did it. And then I filtered by only, so I did store one data 2015. The store one data index is 2015. So I created this new data frame. And then I did only with the days that it's open and plot. And then I know other people simply did this in a single line. That's cool. I just followed like to a T the way that we've been doing it previously, for example. So what does this help us with? What do we see here? It's hard to answer what it helps us with, right? Because there's no like core question we're asking. But so it's just kind of like, what do we see here? Well, we see that we get some sales some days and some not sales the other days, right? Like, I mean, we see big spikes in April, and also a spike seemingly right after New Year's, perhaps. So perhaps like a lot of cold drugs are being sold in those months. Looks like if we correlated this against flu season, maybe we'd see that there was a big flu in Germany in April 2015.
Well, we also seem to see a perfect correlation with customers and sales, which just intuitively makes sense given what sales really is.
Yeah. Yeah.
Surprised to see the standard like min-max difference across. It seems very uniform. So.
Yeah, you're surprised to see a fairly standard min-max difference. Part of that is because when we tell it to plot trend lines, it smooths the edges for us. You can think about it like it's making a bunch of points and of course connecting those points. So if there was a large disparity from one day to another, it's going to go ahead and connect those, even if there's not, minute sales that make it perfectly connected between the two. So that's a good observation. Okay. So now we're going to do autocorrelation. And remember, with autocorrelation, how do we make a variable correlate to itself? How do we do that? Introduce a lag. So what do you think is going to be needed when we call for autocorrelation? A lag. Yeah, we're going to have to pass it some lag parameter. Bless you. So let me introduce resample before I run this. This is poorly ordered. Let me also introduce the concept of resampling, which is, remember, Cody was like, so this is like a group by for the index. And I was like, well, kind of. So resampling is the idea that we can do a group by statement, except we get to determine in that group, are we going to ask for the mean or the median? Like if you group things together, you of course also need to say, do you want the total of those things you group together, or do you want the median of those things you group together? And that's what resampling allows us to do. And in fact, because we're dealing with dates, we pass it D for day, so we could do the mean of all the days in our sample, or W for week, M for month, and A for annual or year. And so it's a nice little way to aggregate things where we select some unit of time, and then we select whether we want the mean, median, or sum based on what we're interested in. So in this case, I could ask for the sales, the data, so we're not just doing store one anymore. The sales resample annually and get the median and the mean. So what is this going to spit out for us? Me, I think you're almost there.
Yeah, the median mean of our feature columns of our sales.
Of our sales. Yeah, our median and mean of our sample of our sales data per year. So that's exactly what we see is each year, and we've grouped everything in those years together, and we've asked for the median of those sales, and we also asked for the mean of those sales.
Here, if you has more than one column in that, you would say
I believe it would operate on multiple columns. If you had multiple things, we could try.
If you do that in our data frame.
Yeah, yeah, we could. Yeah. There you go. So
So the resample is not plucking out just part of the data, it's the whole data set, correct?
yeah, it's smushing different things together. And the thing is how many of them we want to smush together as measured by some unit of time. So in this case, we smushed all the years together. We didn't, sample is kind of a misnomer. We're not sampling from some of those years. We're smushing all of those years together and calculating the median and the mean. So in essence, it's a resample of 100% of our values.
If you had like monthly data, you can resample that day.
If it's a date object, it would be able to process that just fine.
What would the output
It would, so if you had months, let's say you had 1 month or 1 year, and what's your original data set? Is each row a day or is each row a month?
be?
Bless you. And then you ask for days? Yeah, okay. Then I guess you'd be thrown in the air because you wouldn't be able to go backwards. It wouldn't know, unless, it depends. The data frame the data may assume that your month data happens on the first day of every month, in which case you would just get your month spit back at you. Yeah, but in the case that your month data is not just assigned to the first day of the year, it would throw an error. But I'm guessing that actually your date object would just be the first day of each month, would be the number of sales for that month. Is probably how you'd have it formatted. Like his sales are reported 1 day of the month. And even if they're not, you would have to force some day to be when they're recorded.
You can just give it like year month, because this means that it's on like the first second of the first thing.
Well, so in this case, if we gave it year month, since we have every day, it's going to be different. But in this theoretical example where we only have monthly data, and then we ask for
The daytime object treats.
oh yeah, it'll treat it as the first.
Yeah, the first possible.
Yeah.
Smallest thing.
Yeah, and that's actually a problem that I've had. I mean, I really don't like working with dates. It's not a fun thing.
So does the resample function essentially make it a lot easier to get simple aggregates compared to manually creating a month looper or a year looper and then doing?
Absolutely. Absolutely. So it's a
So I could just, if I wanted to manually do this with data, I would by and a column dot me or something like that. It's just so much easier.
yes. Yeah, that's a good point. This is a faster way of saying group by some categorical variable, let's say month. Because we could, in theory, group by a month and then take the mean of that group by statement. Pandas is smart and knows that if you're working with dates, then some of the assumptions of how we calculate things are also going to change a bit. So when we work with dates, there's a nice function that takes care of the group bys for us, and in this case, it's called resample. So I mean, we could also do, so remember I just did annually, our resamples. We could also look at by month. Now, up here, I'm going to resample each day and ask for the mean, and then set an autocorrelation lag equal to 1, which means that I'm asking for how much sales of the previous day correspond to the mean sales of the next day. And so autocorrelation is going to spit out a value between -1 and 1, where 1 is perfectly correlated, they move in lockstep, and -1 means they move exactly opposite directions. So how well does sales of one day correspond with sales of the next day? And it's hardly a correlation. It's just kind of noise if you think about it. Like the amount of sales on a single day probably isn't super predictive of sales on the very next day. And that's what we observe here is it's loosely negatively correlated. Now, oh yeah, so I have an example here where we could sum all of our sales data to see how much there were of daily store sales on a given day throughout that entire year. So in this case, we're doing that same group by, but once we smush together all of our days across stores, because remember we have multiple stores in this data set. So we're taking the total number of sales that happened at these stores in Germany per day. So I just created that as a data frame. Now, before I go to the next thing, are you all familiar with what a rolling mean is? Some are, some aren't. So rolling mean is the concept of taking a mean. So think of a mean. You take a sample of 10 values, and you calculate the mean of those 10 values. In the context of time, we have this benefit where when we get a new unit of observation, that's the very next day, and we can drop the last day, so we continue to have 10 days that we're sampling. And in doing so, if we take this 10 days and we just keep moving it one day, such that we always have 10 days we're taking the mean of, we're taking what's called a rolling 10-day mean. And rolling means are pretty useful because they help us reduce some of the noise, right? Because if you're looking at a daily amount of change, it's highly variable. There's a lot of variance from one day to the next. So a rolling mean allows us to kind of smooth over the trends and see which direction things are generally going. So that's what a rolling mean is. And I was supposed to ask you why it'd be useful, but I kind of just told you. So it's useful because there's a lot of variance and noise from day to day. And in general, it can be beneficial because we can observe trends easier. So one of my favorite hockey stats guys, Micah, he does rolling means of how teams are performing over, I think 10 days is his norm. Actually, I think he does 25 days. It's absurd. 25 games, and then sees how that likely will impact a team's performance in the future. And of course, you can imagine that increasing that range of more games means that you're basing more of a team's performance on that very next day based on a larger portion of their prior season. And if you reduce that window, you said just the prior 5 games, then you're of course ignoring a lot of the season performance in favor of saying only 5 days is best predictive. So when we do a rolling mean, we of course have to set what's called a window, which means the number that range. In the example I gave of the 10-day rolling mean, our window would be 10. And then we also have to say where we want the center of that mean to come from, the very middle day or left or right. And the default is going to be center that makes the most sense of the center of those 10 days. Go ahead and average. So if I do that to our daily store sales, I can see I have the total number of sales across all of the stores in Germany on a 3-day rolling average. Now I could do this for just 2015 by applying simply the 2015 call, and I can also plot it. So it kind of smooths over some of our variance. It's kind of hard to see that we did a lot, but it makes our big spikes a bit more pronounced. So you see this spike on January, or just before January 2014 and just before January 2015. Wonder what that is. So yeah, so the next concept that I want to introduce briefly, don't be too hung up about it, is the concept of an exponential moving average. So the benefit and cost of a simple rolling mean is every date is weighted equally. An exponential rolling average, or an exponential moving average, as it's called, the way that it's calculated weights days that are more recent higher, and they all supposed to be multiples of 10 because the log base that we're calculating. So an exponential moving average in the context of the hockey example I was giving may make more sense because how a team played in the last few games may be more predictive than how they played 7 games ago. In comparison, even. It's not just that those prior 10 games, everyone is weighted equally. Perhaps there was like an injury of a player, or they're on like a hot streak or something like that. The simple rolling average would weight the days without that player equal to the days with that player, by essence of saying, I'm just taking a mean, and each of these values is equal to 0.1 of the total of 10 games. An exponential rolling average, moving average, would favor the games that are more recent to the date that we're observing. Thereby, if there were changes that happened, like a player got injured or someone were on a hot streak, then we would be more concerned with those more recent dates. So here's how to calculate that exponential moving average. Okay. So that introduces the concept of window functions. And we know it. Before I jump into window functions, let me do a quick check of if people recall what the window is. What does that mean when I'm passing window to rolling mean? It's a 3-day range. How long? Span of time. Yeah, all equivalent ways of getting to the exact idea of what the window is. The window is some amount of time of values that we're going to be looking at. So window functions could be anything from rolling means, as we just did here, but we could also do things like rolling median, or rolling sum, rolling min, rolling max, which are all window functions because they're only looking at some amount of the dates in a data set, and we're going to ask for the median or min or max, depending on what we're interested in. So if I had, let's just say this is just my data set. Like this is the sales data, we'll just say. If I ask for the 3-day rolling min, what number am I going to see? Where this is older and this is newer. What's that? For the most recent day. So I have a 3-day. In this case, I'm going to say, I'm going to call a 3-day rolling min, and I'm going to ask relative to this day. the most recent day. What value would I see returned? People are raising fingers. 5, 4. Sorry. This is the day that I'm referencing. sorry. Relative to this day. But everyone's confusion tells me you understand what's going on.
5, but that's only going to be if you set the center false.
Yeah, correct.
Because if center's false, then it'll be 3 days up to and including the day.
Yeah.
If it was true, then you won't be able to get
You're cheating. Yeah. Yeah. We would see 5 returned here. And that's because if we just ask for a straight rolling min of all the values, then, and we said left, which means every value. Don't worry about that for a moment. We're going to see 5 as returned. Yeah, pretty straightforward. Window functions just say apply a lens of some amount of days and then perform an operation on those number of days. And I could say left and include everything backward, right, center, etc. Differences as well. I could do a difference within my window. So I could do the difference of daily stores where the period is 1. What is this going to spit out? Don't worry about like saying the exact values or anything, but I mean you can even run it, and I'm going to ask you what is that? What's that? Yeah. You just use the salesy word for it. Yeah, it's the marginal sales from day to day. But what does that mean? And I prefer to hear from someone on this side of the room, not from the middle. Nicole, you look like you know, but you don't want to say.
No,
You got that
I'm
look.
not sure I know how to say what I think it is.
Give it a shot.
So is it basically you're summing the sales on 2 consecutive days and computing the difference between them?
Yeah, so we're not summing the sales in this step because we've already taken, this data frame is already all the stores for one given day.
Okay.
So your answer is entirely correct if we're thinking relative to the very raw data set we were fed. In this case, we already have the amount of some sales for some day. So the second half of your answer is all that's occurring at this step, which is we're taking the difference between all sales that occurred during on one day minus the amount of sales that happened on the previous day. So yeah, you're looking if I know what's going on, but I don't know how to say it was exactly right. You do know what's going on. And you said it correctly. You added more context even. So I could do the same thing with 7 days, right? Same thing, except it's going to compare the same day of each week, which may be more valuable if you think about it, right? Here's where context as a data scientist matters. The amount of sales difference of one day is going to compare Tuesday to Monday, Wednesday to Tuesday, Thursday to Wednesday, and so on. Perhaps we only care about doing that for Monday to Monday of the next week, or Tuesday to Tuesday of the next week, and so on. Then we would set our difference to 7. And that makes perhaps our difference a bit more meaningful because we control for different things. Perhaps people just shop for drugs more on Monday through Wednesday rather than Thursday and Friday. Or maybe in anticipation of the weekend, they go out and buy a bunch of drugs on Friday. So here's an example from 538 of seasonality that I liked. They showed seasonality in retail by just taking the difference of each month from one to another. And this was in a long article from 538 that will be in the resources if you want to read the full thing for context, where they were basically calling out the Wall Street Journal's assessment of the jobs report. Because they're like, the Wall Street Journal doesn't take into account the fact that retail jobs are seasonal, thereby being like, oh no, like we're losing a bunch of jobs at this point in the year. It's like, well, sorry, bro, that's what always happens. And here's my graph to show that. So here's the difference from one month to another of the amount of jobs in the retail industry. Kind of useful, kind of neat. Okay, now expanding functions. Instead of doing window functions where we're just looking at some values and then peering at one of those values, we can do an expanding function that looks to a window of n values and then performs, similarly, rolling x or min x, max x on those list of functions. So I could do the average expanding from first date till some date specified, or from the sum of the first date till some date specified. In other words, it's basically a window function where you don't have to, where the window isn't peering at some of those values. It's you saying from here to here, and I'm passing you those days, which allows more flexibility in terms of calculating whether it's a rolling mean or whether it's a sum or a min or a max. So same thing conceptually as a window function, but just allows us to perform a different set of operations by specifying the dates. Okay, now the fun part. You have about 15 minutes to work through as many of these exercises as possible. And the first one, I should add a hint. But here's the exercises. The first thing, plot the distribution of sales by month and compare the effect of promotions. And the way that I want you to do that is by producing box plots. And as you work your way through this, if you get kind of stuck, don't worry. This one's a bit more challenging because you're doing a lot of things at once. It's like sales by month, and then also we have this promotions thing going on. So how am I going to deal with that? My hint to you is you can set the hue, the color of one of the bars to be some feature. The second exercise, I want to know, are sales more correlated with the prior date, a similar date last year, or a similar date last month? Are sales more correlated with the prior date, like the 1 day prior, a similar date last year, or similar date last month? The next one, I want to see a plot of the 15-day rolling mean of customers in the store. The fourth, identify the date with the largest drop in sales from the same date in the previous month. That one's also a bit tricky. Compute the total sales up until December 2014. So that will be intent. And then the last thing, when was the largest differences between 15-day moving rolling averages? So you got two things going on there. You got some rolling averages stuff and some differences. So I recommend working top down, but if you get stuck on any one of these for too long, as in you just feel like you're not making progress on it, feel free to skip it, because I think you'll find that 2, 3, and 4 are particularly doable and repeatable. And so we have 15 minutes to work on that, and I'm going to circulate to help people out while we do that. And obviously, feel free to work in pairs. You don't have the answers, do you? Okay. Okay. Where to begin? Oh. I think you with your brain.
No.
Early your brain. For the distribution of sales thing, I recommend using a factor plot. So the same way that we looked at promotions on only days that were open and closed, that's the same type of thing. You should be modifying that factor plot code somewhere.
Each day, like January 14th. If you do, it's like the, like, I don't know, back here, there's not much.
Just about. Are people wholly lost on the first one? No? Yeah. Okay. Well, no, I'm just worried that people are going to get stuck on the first one when 2 and 3 are potentially easier. I get antsy when I'm not helping, basically. Who does that? Ah.
Don't really, because you know it all. It's easy to sleep.
I'm gonna grab some water. How about that? Can you go ahead and show the answer to the first one here?
It's supposed to be just for store one.
You could do all stores. So the tricky thing on this one was the hue thing. You know where Adam is today? Other Adam? It's a bummer. Today's thing is stocks.
Yeah.
Yeah, I was thinking about him the entire time. I was thinking about this lesson. All right, let's run through these. Who was able to check out the correlation with prior date, similar date last year, or similar date last month? Problem. Ah.
Providing you could see is 30 days and New Year's 365 days.
Yeah.
So, looks like it's most correlated with 30 days prior.
And
Negative 0.12 or 1.3.
yeah, we won't have exactly the same values because I'm guessing you.
I did data sales and sample survey by me.
By day?
Yeah, or do I need just sorry, I might have needed this
Yeah.
Then, yeah, 1.2.
Yeah. So what I'm doing, that's totally legit. What I'm doing is I'm creating the data frame of the sales data only when and when they're open to in the open column to resample by day. So grouping all my days together and taking the mean of grouping all those means together. So that values are going to be the average number of sales on a given day. And then I can check, from there it's pretty straightforward. I can just check the lag is equal to 1, which means just check the previous day. I can check the lag is equal to 30, which is just the prior month. And then I can also check the lag equal to 365, the prior year. You look confused as to what I did.
Well, I had done the mean originally too, but wouldn't we actually want to use the sum? Because it's the sales in any given store, so you want to look at the sales across all the stores, right?
Are you resampling and grouping together and then summing all stores?
Data, if I just do data sales, resample, day, how would sum? Then you're going to look at the total sales. It's related to total sales, not the value.
Yeah, and I mean, I made the
Just in
choice.
case there's like data from one store and not another, really. It's
Fair.
really-
Fair.
I guess if you would.
You're gonna run into that problem either way, I think, though. There's
Well, the sum basically it won't matter whether any given store is open or whether there's one is able to still capture everything.
well, you could still. The reason that here's my justification. I don't think what you did is wrong, and I don't think what I did is right. But I chose to do mean because it, in my opinion, helps remove some of the noise of various like aggregate sales data, where if we have generally increasing sales across all stores, then my mean is going to move up. Whereas if I have like sales tanking in one place and sales going up in another, it's kind of hard to say how sales across my drugstores changed overall. So in other words, I took the mean to act as sort of like a denoising measure. So I get a picture of the aggregate, without saying average. So I get a picture of what's like generally happening in drugstores rather than just being victim to perhaps one store doing exceptionally well. What do you think about that? Many stores doing exceptionally well with some doing very poorly. In other words, if I'm trying to compare some correlation, it's generally helpful to think about means for the reason that I'm describing. That if you're doing a resample based on the mean, then you're denoising, or at the very least being less susceptible to a subsample of your stores doing well or a subsample of your stores doing poorly. I get a picture of how Germany drugstores overall are doing is the key difference. Yeah, which is why no way is like right or wrong, but I would prefer to do the mean than a sum. And you found that the month was the largest? Yeah. So you'll note that we agree there. And most predictive in a negative direction. Okay. Plot the 15-day rolling mean of customers in the stores. And I did sales. So I set a rolling mean where my data is customers, and the window is 15 because that's where you specify how many days that you want to observe in some given mean. And the frequency that I look at is day, and then I just plot. So basically taking the code that we saw for taking a rolling mean and then kind of just adding plot to it. Did I have sales written up here? No? No, I'm just dumb.
Joseph, just a quick question on your point two. If you
Here?
yeah, I still think, just looking back at your code, correct me if I'm wrong, that when you're doing your autocorrelation, you're including the closed days too, because you're not explicitly sampling on only open equal 1.
Yeah, correct. Correct. So I mean, I have the potential to filter this to just open if I want.
Yeah, I mean, if you did open equal 1, then your autocorrelation is actually 40% or something, rather than negative 2.5%.
Yeah, you're correct. That I limited to just open, but that I didn't actually use that in any fashion. You're right. So I mean, I could go ahead and when open is equal 1, and then autocorrelate. Identify the date with the largest drop in average sales from the same day in the previous month. Okay, the date with the largest drop in average store sales from the same date in the previous month. That's a lot, right? So here, I'm going to go ahead and take an average. And again, I provide the ability to do the open, but I don't actually take the average, resample on days, and call it average daily sales. And then what I'm going to do is I'm going to calculate the average difference from one day to the next using difference with a period of 7. And then I'm going to look at the head of those values. So step by step, what I'm doing, I'm first taking the average of the days. So I've condensed it into daily values. And then I'm going to look at one day compared to that previous day in the previous by week by taking the difference and storing that in the data frame here with the column name difference versus last week. And then I'm going to look at the head of that column. That was a pretty involved one. Yeah, difference is the difference between is taking is subtracting at its core, and it's taking the difference between before worrying about which values, the most recent value in a data set versus some value prior to that. And we get to specify what that some value prior to that is. So if we specify a difference of 7, we're saying take my value here, this day, and then look to the value 7 units prior. And in this case, since we're working with days, it's going to be 7 days prior. And then it's going to subtract that latter one from my more recent one. And I'm going to post all these answers. So if you guys are, I think some people are maybe squinting a bit. Yeah, that would make sense. Hold on. The date. Yeah, resample to 30. The date in the previous month. Yeah, so I mean, you could resample to 30. That kind of spoils my fun because I was going to show you that the day actually ends up being Christmas Eve. So when I post this, I'm going to change this to week. All right, so that we can have the code be the same. We can still see Christmas Eve is really significant. Did everyone see what I did there? Is that okay? So basically, the window, we adjusted the window. Where the window is week, it's 7. Where the window is month, it's 30. And I shifted the goalpost so that I could keep looking at Christmas Eve. So if I look at it and I sort it, there it is. Huge difference. So people aren't buying their drugs on Christmas Eve. It's probably good, right? Okay, so compute the total sales up until December 2014. So I'm going to take my total daily sales, again, from my larger data set. In other words, condense all of my stores. So I just have all the sales. I'm going to sum them together. So the total number of sales that happened on one day in Germany across all stores is what is in total daily sales. And then I'm going to do an expanding sum where I get to set the parameters for how big my expanding sum is. And the parameter I'm going to set is December 2014. So this is expanding sum example. You get to pick the date at which the window stops. It's kind of like how expanding sum is used. So BAM, total daily sales is a data frame again of resampling by day. So grouping together all the stores for one day and summing their sales. And then I'm going to do an expanding sum, which means add together every single one of those values of total daily sales, because that's what's in this data frame. That's the values we're passing in. Up until when? Up until December 2014. And that's an index. And the last one, the tricky one. When were the largest differences between 15-day moving rolling averages? So we need two things. We need the 15-day moving rolling average, and we need to take a difference of those 15-day moving averages. So what I did was I set a total daily sales window of 15, took the rolling mean of that, and then I said I want the difference 1. Why did I do difference 1 here if I'm doing 15 days?
Because it's computing the 15-day rolling averages, and then you want to compare it to the previous one.
Yeah, exactly. So this gets back to the crux of your question of what difference is. Difference looks at our rows, and where you set the difference parameter is how many rows back it looks. In this case, each one is already 15 days. It's a 15-day rolling mean already. So if I set a difference of 1, it's going to look to just that. And so this one's just going to look to that, and so on. And then I sort on sales so that I can see the largest to smallest, or smallest to largest. Yeah, but I'll post this so everyone can also have a look at it. And then I went ahead and added a lab. So I'll send that out. The lab is pretty, so you'll note that these exercises, like this is fairly straightforward in that it's like, here's how to do different commands in Pandas that are useful for mutating date values, which means that inherently the lab is also going to do some exploratory data analysis of things that interest you. And in this case, we're going to do EDA on 5 stocks that you like, or you want to investigate, and export that data from Google Finance or Yahoo Finance, if that's your preference, and kind of check out how things moved. So like autocorrelation, windows, rolling means can be kind of interesting, especially if you think about some stocks. For example, if you look at stocks that are event motivated, it can be particularly interesting. Event motivated stocks. I'll go ahead and post this code.